Hey class, Adam Ward here. One more short-term storage analysis, something called the holdback function. And this holdback function is something that comes from a Danckwerts paper from 1953. And conceptually, the idea here is how much is the mass deviating from plug flow? And plug flow is what we mean by a system that would have perfect advection. So in a plug flow system, a signal that's put in at one end is simply translated to the other end of the system. And so you could think of that like setting your breakthrough curve on a conveyor belt. It doesn't skew, it doesn't spread, it doesn't change, it simply moves through the system. And so what Danckwerts does with this holdback function is ask, how much is our system like perfect plug flow? So if 100% of the mass moves through the system, just like it's on a conveyor belt, it doesn't spread, it doesn't get delayed, all it does is simply move. 100% of it moved, so 0% of it was held back, you would have a holdback value of 0. In contrast, the other extreme would be the mass never makes it to the outlet of the system. In other words, all of the mass takes longer than that plug flow time. And the holdback would be 1. 100% of the mass was held back more than you would expect from a plug flow system. Now that sets up a continuum. So holdback is going to be a value that ranges from 0 to 1. Very low holdback numbers would be things like pipes flowing full, concrete channels. Very high holdback would be things like estuaries, where we expect primarily diffusion and very little advection. Streams tend to fall somewhere in the middle. So conceptually, holdback is describing how much do I deviate from an advection-only system. Now the way we calculate that can be a little tricky. So the plot that makes the most sense to me is borrowed out of the paper here. On the y-axis, the cumulative fraction of mass exported. So this starts at 0 because no mass has been exported initially, and it's going to go up ultimately to a value of 1. And so Danckwerts uses a capital F, and so we're going to stick with that. So this is the integral from 0 to time t of the normalized concentration. On the x-axis is time normalized by that median arrival time, m1, that first temporal moment. And so what we're really looking for is the point at which this curve crosses this line. The intersection of those things. What fraction of mass has passed by me at one advective time scale, or one median time scale? The way you calculate that is to take 1 divided by that first temporal moment, so 1 over m1, and you multiply it by the integral from time equals 0 to time equals t, or to time equals m1 of that cumulative function. Shoo! So that's the mathematics of it. What you're functionally doing is you're asking, hey, how big is that square, or how big is that shape that I'm hatching in with yellow right now? Right? That gives you your holdback function. So you'll calculate holdback, and then you can interpret it on a scale from perfect advection, holdback equals 0, to 0 advection, no advection. So 100% of mass is held back. So a low holdback means a strongly advective system. A high holdback means processes other than advection, things like dispersion or transient storage, are increasingly important. So based on this video and the associated manuscript, you ought to be able to both calculate and interpret holdback function for your solute tracer study. Thanks for sticking with me, everybody.